This is about closed-loop steady-state error of a unity feedback system. Terminology includes system type, position, velocity, and acceleration constants. Here is a unity feedback closed-loop system with reference signal input and closed-loop signal output, and the error signal, which is the difference between the input and the output. The zero error indicates that the output signal tracks the input reference perfectly. Standard open-loop transfer function has some numerator and some denominator in factored form, where s to the n power is the key to steady-state error calculations. N is the number of free integrators. N equals 0 means no free integrators or a type 0 system. N equals 1 means one free integrator or a type 1 system. N equals 2 means two free integrators or a type 2 system. The number of free integrators, or type number, affects the steady-state error. The steady-state error is also affected by the input signal. Input signal might be a unit step, or a unit ramp, or a unit parabola. These are standard inputs. These are the graphs of those signals. And the time domain equations for those signals. And the Laplace transforms of those signals, the S-domain versions. Here's a table to summarize our steady-state errors, that is, the error at t equals infinity, based on the system type number and based on the kind of input signal. A zero steady-state error means that the step and ramp can be tracked perfectly for these system types. A steady-state error of infinity means that the system cannot follow a ramp or a parabola for these system types. Type 0 system can follow a step. Type 1 system can follow a ramp, and a Type 2 system can follow a parabola, but there will be some non-zero steady-state errors given by these expressions, these formulas. Steady-state error is 1 over 1 plus kp in this case, where kp is the position constant, calculated this way. Steady-state error is 1 over kv in this case, where kv is the velocity constant and can be calculated that formula. The steady-state error is 1 over ka, where ka is the acceleration constant and can be calculated this way. In summary, we have a unity feedback closed-loop system with an open-loop transfer function that has some number of free integrators, which indicates the system type number. There are three kinds of input signals, which result in closed-loop steady-state errors. Which can be calculated using position, velocity, and acceleration constants. We can visualize the steady-state error. Let the top signal be the input reference and the output signal is the bottom shadow. Then the difference between those two is the steady-state error.